This lecture will cover basic concepts about random variables and probability. A random variable reports a quantity with some uncertainties. For example, my heart rate is a random variable. Every time I measure my heart rate, I get a different observation of this random variable. A set of observations form a sample. The total number of observations in the sample is the sample size, usually denoted as n. A random vector groups multiple random variables into a vector. We can think of a random vector as a d-dimensional random variable, where d is the number of elements in the vector. For example, a three-dimensional random variable x includes heart rate, blood pressure, and blood glucose level. Each element is a unique feature in this random variable. An observation of this variable includes three values, one per each feature. There are different types of random variables. A continuous random variable takes any real value in a range, for example, blood pressure. A discrete count variable takes non-negative integers, for example, the number of visits to a hospital. A binary variable takes either 0 or 1. It represents one of the two possible outcomes. A categorical variable represents one of multiple classes. If there are D classes, we often use a D vector. One and only one element in this vector is 1, and the rest are zeros. This is also known as one-hot encoding. For example, we have three classes here: 1 flu, 2 cold, and 3 allergy. To represent the first class, the first element is 1. To represent the second class, the second element is 1. To represent the third class, the third element is 1. For a random variable, the distribution of its value is often described in terms of probability. For variable x, we can look at a specific range A and count how many times observations of A fall into this range. Divide this count by the total number of observations, or the sample size. This ratio is an estimate of the probability that x belongs to A. We can indicate this estimated probability as the height of this bar and repeat the same analysis for different ranges. This bar plot is often called the histogram. When we estimate probability using data points in a sample, we want different data points to be independent and identically distributed. Being independent means the action of drawing one sample is independent of the action of drawing any other sample. Being identically distributed means that different samples are drawn from the same distribution regarding the same random variables. When we have a large sample size, we can divide the range of x into small bins and plot the histogram with higher resolution. The top of the histogram traces a smooth curve. When we have an infinitely large sample size, and this curve converges to the probability density function. The probability density function is non-negative and has a range between 0 and 1. When we choose a threshold t and ask what is the probability that x is less than t, the answer is the integral of the density function up to x equals t. This integral up to a threshold is also known as the cumulative probability. It's important to know that the cumulative probability is always up to 1. The illustration here is for continuous variables. For discrete variables, we replace integral by sum, and the sum of probability always equals 1. For a random vector or multidimensional random variable, the probability density function describes the joint probability of every element in the vector. For example, for a 2D continuous variable, the histogram is a 2D bar plot, and the probability density function is a 2D surface. It can also be shown as color-coded contours, where points on the same contour have equal probability density. It's possible that the probability of one variable depends on the value of another variable. This dependency is often captured by the conditional probability. For example, here shows the samples of two random variables x1 and x2. Clearly, the probability of x1 depends on x2 and vice versa. This shows the joint probability of x1 and x2. We can set the condition by fixing the value for one variable and then evaluate the probability of the other variable under this condition. The top shows the conditional probability of x2 given x1 equals 1. The bottom shows the conditional probability of x1 given x2 equals 0.8. Setting the condition differently change the conditional probability distributions. Given the joint distribution of x1 and x2, we may ask what is the probability of x1 taking a specific value regardless of the value of x2. The answer to this question is called marginal probability. The marginal probability of x1 is the integral of the joint probability over x2. The marginal distribution of x2 is the integral of the joint probability over x1. The joint distribution of x1 and x2 can be expressed as the conditional probability of x1 given x2 multiplied by the probability of x2, or the conditional probability of x2 given x1 multiply the probability of x1. The two ways being equivalent leads to the Bayes rule. Here we summarize key concepts about probability and how different types of probabilities relate to one another.